You probably know, too long. I lived up in Nome for 17 years, did a lot of building science and building energy efficiency work, and dabbled in heating systems forever. And when I got down to Seward, I retrofitted a little house, and my goal was a heat pump. I've always wanted to do a heat pump, so I bought the only thing I could find in the North American continent at the time, and it was pretty good, but not as good as what we have today. So what I really like to do is just do a nice overview. It's a small town, small group. Got a question? Going too fast? Going too slow? Somebody just, keep it rolling. So that first slide, when I talk about electrified sewer, it's really, I'm kind of into the climate change thing. I sort of believe it's real, and I really think we ought to be cutting down on oil. And our two big oil consumption is heating our homes and driving our cars. And one way to address the heating oil is with a heat pump. And what's really incredible is we're pretty much showing that we can be lowering our heating bill by 20-30% with a heat pump. At the same time, reducing our carbon footprint by 60%. And we get to support the electric utility instead of big oil. So we get to actually support our local electric rates and stuff at the same time. So primarily I'm going to be talking about what we call a mini split heat pump. And they call it a mini split because we have an outdoor unit and we have an indoor unit. And in between, inside this chase, are a couple refrigerant lines that run hot refrigerant to the indoor unit and then back to the outside. Average cost, $3,000 to $4,000. You can talk to Darian some more, talk to the electrician sometimes is sort of the big unknown. Darian kind of knows what he can do, but there's a few players in there. So really, what is a heat pump? It's really a really efficient electric heater. And what we're doing is it's no free lunch though. We have to take a kilowatt of electricity in this example. And we're going to fire up this heat pump, which you'll see shortly, it's really no different than your refrigerator in your house. That's exactly what this is. But with our heat pump for heating our homes, we're going to put that 1 kilowatt in there, and it's able to pull out, in this example, 1.5 to 2 kilowatts of heat out of that cold air. I'm not going to explain the magic of refrigeration. If Darian wants to take 8 hours and try to get it across, that's fine. I leave it as kind of magic. So in this case, we're actually getting 1 kilowatt of heat from the electricity and 1.5 from the outdoors. So we're ending up with 2.5 kilowatts of usable heat inside our house. It's like 1 electric heater or 2.5. You get a whole lot more heat out of 2.5, or 2 heaters on high and 1 on low than you do out of 1 high. More chairs. Oh, makes sense? Let's next. So here's a heat pump. Basically, it's this magic compressor that plays with this refrigerant, and there's a coil on the inside and there's a coil on the outside, just like your refrigerator. Your refrigerator freezer's got coils on the inside, and it's got, the older ones had the coils in the back. The one that coils in your refrigerator pull heat out of the freezer and dump that heat into the back of your refrigerator. That's why it was warm back there. That was heat that came out of your refrigerator that created that heat. And a heat pump can go either way. So it's kind of nice. In the summertime, we can actually run that heat pump in reverse and it becomes an air conditioner. Next. One of the things I really like about heat pumps is if we look at our oil heating system, here's 100% efficiency. But But we're pretty much there. We really can't fine tune our boilers anymore to get any more BTUs of heat out of a gallon. Same thing with gas, we're pretty much there. But look at heat pump. Here's where we're at today, 250 to 300% efficient. But theoretically, we could be up here. If we had that magic refrigerant and that magic compressor and a magic fan and stuff, in theory, we can be up here. So we're going to gradually be marching up. I don't think we're going to see any great revolution in the coming days or months or years, but that's kind of where we're going. Electric grid, and the more renewable we get, obviously the cleaner the heat pumps get. And again, that CO2 reduction, which I think is pretty critical, is like 60%. So just a little lingo. We've kind of gone from mini splits to now we're talking about cold climate air source heat pumps. Air source meaning we're getting the heat out of the air versus say like the Sea Life Centers, getting theirs out of the ocean. Or ground source, we're getting out of the ground. And the cold climate part, what that's really telling us, if you see that, it means it's been tested down to like 5 below. Some of them have been tested to 15 below. And so it's telling you you're not getting one that's designed for Florida. You're getting one that's designed to actually work in cold climates. So again, we're talking primarily about mini splits. And they can be just like that single head that we saw in that first picture, or some of the little larger units will have multiple heads. And we can talk a little bit about the pluses and minuses of those. Pretty much they have very minimal ducting. They just have those refrigerant lines run into the separate little fan coils. So it's not like that central air conditioning where you have your furnace fan, and you got these big coils in there, and you're doing the whole house. I also want to talk a little bit about air to water, because that's what I've been playing with a bunch as well. And basically it's the same outdoor unit, only instead of running this warm refrigerant up to that little fan coil up on the wall, it's running it through a little flat plate heat exchanger that's taking cold water out of the bottom of my storage tank, taking heat out of that refrigerant and putting it into my tank. So I'm making warm water. Not hot water, but making warm water. And there's kind of several different types, which we can get into a little bit more if we have time. But and so because I'm only making warm water, I have a radiant floor in my little house. So that's perfect. 100-degree water, it's happy. I boosted up with my regular domestic hot water heater up to the 115, and that seems to work fine. And there's also fan coils, I can show you one. So that's typical of air to water. There's a bunch of different refrigerants out there. I don't know if Darian's played around with very many commercial units, but the big boys might have, I don't know what, a dozen different tanks of different blends of refrigerants, and they never have the right one for that particular job, so they end up with one more.
It's always changing.
Yeah.
I made a new one yesterday.
Did you? Yeah. And it's this whole battle about, before it was all efficiency and safety. Well, now the environmental side, because we know how bad our man-made refrigerants are that we have, we're looking at the environmental considerations as well. So these blends are changing, trying to maintain the efficiency and the safety, but improve the environmental aspects. A couple more little terms you're going to see if you ever do a little Google search. COP, coefficient of performance. That's really the energy output divided by the energy input. Like in that example, we put in 1 kilowatt of electricity, but ultimately we ended up with 2.5. So that had a COP of 2.5. Essentially 250% efficient over a straight electric. The other term that's very common in the heating side of heat pumps is that HSPF, Heating System Performance Factor. Just another American way of confusing the world, but what they're trying to do is come up with a seasonal average, because I'll show you a graph where the COPs vary depending on the outside temperature. Because the more it's got to take that heat out of that cold air, the colder that air is, the harder it's got to work to get it up to temperature so it's usable. So it varies, right, over the course of a winter. So that HSPF is trying to give us sort of the seasonal average, which is really good. Unfortunately, it's for region 4, which is like North Carolina or something. But they get some cold weather, as cold as we get actually, but for such a short period of time that it kind of shifts this number a little bit. But it's a good reference, we hope. For those of you who've been in the refrigeration world, we used to always talk about tonnage. It's a 1 ton or a 3 ton. Well, they kind of got away from the ton world, and now you'll see them rated as kilowatts. 12 kW, 9 kW, 15 kW. And really the difference is a 12 K is essentially a 1 ton. And that was a cooling number. And the other thing, they talk about capacity ratings. And they're going to give these to you at 47 degrees. Like, who really cares how much heat you can get out of your heat pump at 47 degrees? But they also give you ratings down to 5 degrees as a very standard. That's where I'd recommend you just skip all the other stuff. Okay, here's what it can do at 5 degrees. That's kind of what I'm looking for. Because if you look at this neat site here, they have listings of hundreds of heat pumps now. Hundreds. Some of them are really the same with different brand names. But you'll see that some 12Ks are no different than a 9K rated heat pump. Because they rate these things, I don't know how they rate these things. So that's why it's just important to kind of go down to that capacity rating at 5 degrees and compare one to another one to another one to decide. Oh, a few pros and cons. Less expensive. I'm sure that's why some of us are here. You know, when I remodeled my house, that old boiler went, the fuel tank went, the fuel lines went, gone. No more fire inside my house. Hoping no more smell of that oil. No combustion going on. Again, 2 to 3 times more efficient than conventional. And that little mini split, I'm telling you, when it gets warm, when we had the smoke. Anybody who had a mini split who could keep their windows and doors closed when it was hot out and could run that air conditioning, even if it's just for a couple of weeks, it was a treat. Well, the cons, of course, $3 to $5 grand, depending on what kind of installation you have. Mini splits can't produce any domestic hot water. They just make warm air. So we still have to deal with our domestic water loads. And if you got a lot of kids and a big family, that can be a pretty significant number. Very limited heat distribution, and that if you just got that one mini split head, it's like having a Toyo stove or a wood stove. It's really just, it really just wants to heat the open area. Depending on how insulated your house is will help determine what that temperature of that back room is. But we can go to multiple units, multiple heads. We can do it. It's just a little money. And here's one that we've heard forever, except they always said, well, heat pumps don't work in cold weather. No, they work just fine in cold weather. They just don't produce quite as much heat as they would otherwise. And their efficiency drops a little bit. I can show you a slide of that. So here's the output. This little line here is like a little Toyo stove. doesn't care what the outside temperature is, right? It can just wide open, this is what it'll give you independent outside, but a heat pump, and this was the Fujitsu, and this is manufactured data, I think, but it shows that as here's the temperature from minus 20 to 50, it shows how your output drops ever so slowly, constantly, and at minus 5, that was their rating. So they stopped giving us any data. In reality, it continues down this curve for, I don't know, minus 15. I think at Fairbanks they've run down to minus 20. I assume at some point the refrigerant doesn't boil anymore. So there must be some number down there that they don't work. But for us, this certainly is more than sufficient for Seward's climate. Well, here's what happens to the COP, sort of the same deal. When it's really warm out, we have a really high COP, and as it gets colder out, the COP drops. And it drops to a point where, even here it's saying, at below 0, we're still at a COP of 2, which means we're still getting twice the amount of energy out of that kilowatt as we would out of the electric heater. Now, this is kind of manufacturer data. I would be dropping that down a little bit. But it's the same line. And we're going to find that around 10 degrees, 0, the economics just really aren't there as much to run. But they still work. I mean, it's just the little heat pump's just going to keep doing what it can do, but it just can't do as much. And here's why I think Seward is kind of special. I have an old utility manager that thought Seward was special too, but for different reasons. And so here's a load profile of what Seward is. You know, we get a little bit above 60 degrees, but the bulk of our heating is right here. Yeah, we get some down here, but not too much. So if we're going to say, you know, the economics past 10 degrees isn't so good, that's really a small chunk of the heating that we might have to supplement with something else. If this was a really cold climate like Fairbanks, you would see a whole lot more of that darkened area all the way down to 40 below. Well, the heat pump just isn't going to do it for them at that cold temperature. So do heat pumps work in Fairbanks? Absolutely. They still have a really big chunk of temperature, outdoor temperature, where the heat pump can do a lot of work. They just can't take care of that below 0 stuff. And so again, it's that fact that we've got those moderate coastal temperatures. We've got relatively high fuel oil costs. And we've got good winter electric rates. That combination kind of makes us special. Homer has higher electric rates than we do in the winter. And it kind of dings their economics significantly. And if you're on natural gas, I'll show you where it kind of makes the economics of heat pumps look pretty poor. So I just want to throw a slide up on some of the new air-to-water heat pumps that we can see in the U.S. If you go to Asia, you go to Europe, there's almost as many air-to-water heat pumps as there are air-to-air heat pumps, but not in the U.S. But we do have a few. Let's back up. Can you back up? Yep, this one's quick. This is called a Sandin, and so it's the same kind of outdoor unit as a mini split. And they're basically just taking water from the bottom of the tank through a heat exchanger in here, and then running the hotter water, back up into the tank. And so it just circulates through this unit and creates a tank full of warm water. And the CO2 is kind of a nice concept because in terms of refrigerant being bad for the environment, it's no worse than all the other CO2 that we have out there. But they work at very high pressures and technology is coming. You'll see, if you just did an air-to-water heat pump in Google, you'll probably see Arctic come up, very similar. And Chiltrex is another one. And here's a Canadian one called Nordic that's kind of more of a commercial looking. It's a heavy duty critter. I know the engineer down in Juneau is starting to install a bunch of these, so something to watch for. Next. So here's my little Chinese heat pump. In that outdoor unit, these are refrigerant lines going down into my crawl space. Gary remembers this little box. And right here is this flat plate heat exchanger that's taking the heat out of that refrigerant and it's pumping it with this pump, pumping it into my storage tank here, creating that 50 gallons of warm water. So now I get my domestic water and my space heat. Here's, I think you might even be able to buy these in Anchorage at Lowe's or Home Depot. This is called a heat pump water heater. It's essentially a tank, electric tank, with a heat pump on top. And it's taking the heat out of room air and dumping it into the tank, making hot water.
There's cold air coming out.
Well, then you got some cold air coming out, which you got to reheat in the wintertime. Now, if you're in Florida and you're air conditioning anyhow, this is about as good as it gets because now you're basically cooling your house and heating your domestic hot water. We can talk more about it, but there's some places where this would work. 3-4 months out of the year, you could be running it outside. Or if you got a wood stove, you could essentially be heating your domestic water with the heat off of your wood stove. You just got to remember you got to replenish the heat that you're stealing to put in that tank. So how do we pick a heat pump? Well, I do not recommend doing what I do, going to my buddies in China and ordering a sample. You're kind of living on the edge a little bit. But sometimes it's all I can get from my curiosity. So I really recommend, if we stick with the name brands, they're not going to sell you junk. And Mitsubishi is a big name, Fujitsu, Panasonic, Daikin, Gree, and some of the big heating air conditioning companies like Trane and Carrier, they picked up one of those heat pumps and put their label on it, but you're going to get all of their dedicated service and training and stuff. So I think you need to go that way. And then we got to be looking at this HSPF and see what kind of performance, because you can get the whole range. You can get really crappy ones and you can get really good ones. And pretty much all of these top brands will sell a standard mini split that has an HSPF of over 14. So there's no reason to really go much lower. Now you see that mentioned single head? They seem to be a little more efficient than the ones that have the one outdoor unit and multiple heads in different rooms. So you lose a little efficiency, but you gain on distribution. So you're still way ahead of the game with oil, whether you go with single or multi. Sizing is kind of a deal. Bigger is not always better. If you got a small place, small heat pump, and taking care of those really few cold days with something else may be a lot more efficient than trying to get something that's going to take care of that one day out of the year. And I'll show you some slides. Okay, a little economics. Here's a magic number. This works for Seward. It takes 12 kilowatts of electricity into that heat pump, on average, over the course of the year, to generate the same amount of heat as 1 gallon of fuel. 12 kilowatts. If you got propane heat, because propane's got a lot less heat BTUs in it only takes 8. And electric, when you're at that 2.5, it only takes like a third. of electricity to make a kilowatt of electric heat. Here's a number that my buddy Alan came up with, 1,350 kilowatt hours to save on a cord of spruce wood. So we can kind of start looking at the economics of our wood burning. So if we kind of take these numbers, 12 kilowatts of electricity to generate a gallon's worth of heat. Just kind of burn that in. So here's this example, 12 kilowatts. Well, you know, we have a winter rate and a summer rate, and so we're going to use a little bit of that summer rate in the spring and fall. So I like really round numbers. You may notice I kind of round things so I get zeros, so I can do the math better. So we're around, on average, over the course of the year, our electric costs are about 20 cents a kilowatt. So 12 kilowatts to make 1 gallon times 20 basically means it costs us $2.40 to produce a gallon of oil overall. During the warmer months, it actually costs us less. During the really cold days, it actually costs us a little bit more than that, but on average, $2.40 a gallon. What are we paying today? Anybody know? I don't even like to call them up anymore.
$4.49.
$4.49.
Without
fuel
tax.
oil?
Yeah.
Without oil, yeah, without tax. It was $4.49 because they just filled my shop tank. Yep.
49.
$4.49.
Yeah. So, you know, a month or so ago, we were a little over 3 something a gallon, I think. So, you know, to do the math, 12 times our 20 cents seasonal average for electricity costs us $2.40 a gallon. So if we were paying $3.30 a gallon minus the $2.40 we had to spend on the electricity for the heat pump, we're saving about 90 cents a gallon. And a typical heat pump running, you know, letting it work, we should be saving somewhere in the 400 to 500 gallons a year. Now, if you're only burning 300 gallons of oil a year in your little house, you are not going to save 400. Okay? But if you're burning 2,000 gallons of oil a year, you might be saving 800 gallons of oil. But if we kind of stay conservative, well, you know, now we're kind of talking $400 or $500 a year savings. Now we got today's price up. See, I used $4.25. We could have done some math.
Could have gone to 450.
Yeah, could have gone to $4.50, but $4.50 times 12 isn't a tough number to calculate. But at $4.25 minus the $2.40 for the electricity, that's $1.85 a gallon we're saving, over twice what we were saving before. So the sensitivity of what you're paying for oil is what we're trying to show here. What the price of oil is going to be over the next 15 years of the life of your heat pump, I'll let you guys figure that one out. Okay, the other little thing I had to put in here, the the electric utility that we own is basically making $1.20 for every gallon of oil that we displace with our heat pump. So we're contributing $1.20 to all the other ratepayers of Seward. So that should really make us sleep a lot better at night.
Can you explain that a little further for me?
Which
How I'm helping my fellow ratepayers.
Okay, well, we're using 12 more kilowatts of electricity than we did before, right? For every gallon. Well, the electric utility's got to buy, you know, power from Chugach, and then they need to have a budget to distribute all that power and maintain. That's about 10 cents a kilowatt, is what it's costing them to run the system. Well, 12 kilowatts times 10 cents is like $1.20 that they're putting into the piggy bank for every gallon that we save. And that's not bad. I mean, that's good. I'd rather see it go there than off to big oil someplace, right? So here's just a little table. We don't spend too much more time, but again, heating oil at 12 kilowatts ended up costing us $2.40 for the electricity. We were paying $3.30. Now we're saving $90. And then there's propane, electric. spruce wood. That one cord, remember that 1,350 kilowatts? Well, times 20 cents, that's $270 a year you're gonna spend running that heat pump to displace a cord of wood. And if you were paying $300 a cord, you're actually gonna save $30 a cord by running a heat pump instead. Now you might have a heart attack because you're not staying in shape, and there's all kinds of great benefits of going and if you're getting your own wood, that $300 maybe doesn't mean anything, but if you really are truly buying cords of wood for $300, it's kind of something to think about. Still an excellent backup heat source, so don't get rid of it. And it might be perfect for those really cold days. And a little slam dunk, propane and electric resistive heat. It's a no-brainer, you don't even need to do the math. In terms of the carbon impact, we just kind of put one slide in there. And this was, we just did this presentation at Homer Electric, and my good friend Alan kind of did it for Homer Electric. And technically our Chugach Electric kilowatt, Chugach has got a little more renewables in their mix, so our CO2 production is a little bit less than Homer's. But here's what the heat pump's generating in CO2 tons per year versus heating oil up here, propane, natural gas, and electric resistive. Now here's kind of an icky one, burning wood. And we got that highlighted here in a different color, and a big note kind of on the complicated side. And if you're in the whole carbon world, what happens to that dead tree? If you leave it stand for 20, 30 years, that carbon stays kind of in the tree. If you cut it down and burn it tomorrow, you put that carbon back into the air fairly quickly. I'm not going to get into that argument or discussion. It's just, obviously, if a tree can stay for a long time, but if it falls down close to town here, it's gone in 2 years. It's rotted, right? It's done its thing. So that number is kind of something you don't have to worry too much about. Let me sit down here and do this. So we have this great little heat pump calculator. This was a heat pump calculator that Alan Mitchell put together, and as you can see, there's some of the sponsors, Homer Electric, Alaska Housing, and some of the other utilities. And what it's basically able to do is he's taken all the weather data and fairly updated fuel data. We're not going to see what we got going on this week. They don't update it every week. But we're able to pick a community that we pick Seward. And now it automatically knows the weather data. It wants us to know whether we're residential, because it knows the residential rates. You can kind of check monthly charges. This is kind of our average cost. And now it starts asking us a few questions about your building. How many square feet? Anybody want to yell out a number?
3,300.
Oh, jeez.
Oh, jeez.
How about something at half that?
You asked for a number.
I know, but I want something on the average.
All right, 16.
16. I'm gonna stop asking. So what it's trying to do is kind of figure out how much, what quality a house is. So we can, whether it's an older 2x4 house, 2x6, or if you got something new with better than 2x6, just taking the stab. Then you put in what type of fuel you're burning, and whether or not that fuel is being used for any other thing. And here's where we can put the price of fuel. We'll leave that for now, and we can go back and change it. The efficiency of your existing heating system. Assume we got a standard boiler in there. You can go ahead and change these things, go back and forth. Here's where if we know exactly how much oil you burn, it can be a lot more accurate in terms of what it can do. Because it's taking just a few numbers and trying to model, you know, what I used to do as an energy rater, spending hours calculating stuff. But if we don't know for sure, just leave it blank. Then it goes through some stuff for the northern utilities with PCE and stuff. We can kind of ignore that. You can tell it what temperature you want the inside of the house to be. The cooler you keep your house, the less it's got work it's got to do to provide that heat, so it's actually a little more efficient. Whether your heat pump is a single head or multi-zone, you can play with that. Then we can either use a simple heat pump model, or we can go to advanced, and it's got hundreds. It takes that list of heat pumps, and so we can actually go through and pick a heat pump that Darian recommends, or somebody online recommended, or you went and did some research and well, let's try a Daikin. And here's where you can actually go, and you can go back to this and I'm going to try a different one. What's a good cost for a Daikin?
About $3,000 for a 9K.
3.5?
Installed or just the actual unit?
Well, installed.
Installed, yeah. $3,000, $3,500, somewhere in that.
Okay.
ballpark.
And again, and here, if we were getting rebates, which is a discussion that I'd love to have, but
Sustainable Seward, what Phil's alluding to is Sustainable Seward is encouraging the city to look into a heat pump rebate. I don't know if Rob is here. I've never met Rob Montgomery, the utility director. Nobody's volunteering that they're Rob. So what Rob was going to say, had he been here, was that the city is looking into it. They are not committing yes or no to it, but they are looking into a rebate. Lots of utilities around the state have heat pump rebates programs. So
how much did I say the utility was making on our gallon of oil? $1.20. We're saving 90 to $1 or something, and they're making $1.20. It's kind of like, geez, guys, you know, maybe we ought to kind of like split the cost of this thing, and everybody wins, because the more heat pumps we put in, the more the kilowatts they sell, and the less
So
carbon.
we're hoping that their investigation turns out to be something positive that they want to do, and that we'll hear about that.
But I let up on them. I was kind of mean and nasty, and they wanted to research, so I kind of backed out a little bit.
So do you know, down the road, say 10, 12, 15 years, when electric vehicles become more on the scene here and stuff, are there any projections on the change in cost of electricity in Seward or any place in?
Because you're talking upgrading transmission.
It's only going to
lines,
go up.
right?
It's
Well,
only
just,
going
you
to
know,
go up.
right now,
But that's a whole nother discussion,
Yeah.
Mike, but
Right.
there are lots of things that can happen without
Exactly.
huge amounts of money for upgraded transmission
No, I
lines,
understand.
like batteries and small-scale renewables in our area. But
I think for us, they're just going to up the voltage of the
we
power line.
I
digress.
think they're doing that already.
Right. So
My
that's
guess,
in the plan.
it will go up, but not near as much as
Right.
fossil fuels.
And it's gonna be gradual anyway.
Right. So anyhow, we could play with that, and you can go, okay, well, if the utilities was giving us a rebate, we could, you know, see the benefit. Or if they had some low interest loan program, especially for lower income, hey, we can give you this low interest loan, and you can pay it back on your bill. So this software has all of this built into it. If by chance, if you're up in Fairbanks, you may just want to pick some months you don't want to run it. And then we get to, is this building, you know, are you heating it like with a toilet stove or wood stove, and we're not going to worry about distribution? If it's no, they want to know how much of your exposed area of your building you have. You can kind of play with that. You can say, well, I'm going to leave doors open and stuff. They actually ask you, are you willing to live with 5 degrees cooler in the back bedrooms, 10 degrees cooler? Because they're trying to figure out how much heat are we going to be able to use out of this heat pump that's just pumping heat into the main living area. You know, if the doors are left open or if the doors are left closed. Play with all of that, your sewer and sales tax. You get down here and you hit calculate results. So it's saying for that particular house, putting in that heat pump, you're basically gonna earn 14% on your money over the 14 years of your life. It's just like having it into an IRA or something, an investment account. That's a pretty nice return. The net present value says after you've paid off all of this, your heat pump, with a little interest, you're still gonna make, in addition to that, $2,600. So it really is showing a pretty good deal. It's saying this particular house is gonna save like 448 gallons of oil a year. Here's your electric increase, and that should work out to somewhere around 12 kilowatts. I'm not gonna let you do the math. And it's estimating that COP, that coefficient of performance over the season, a 2.6. And we've been dinging that down a little bit over the last 3-4 years, going down. We were thinking it was going to be closer to 2.8. And it's just some of the data that we get from other places and stuff going, that's sort of maybe closer to the real number today. As they improve the efficiency of their units and the smarts, that could all go up. A little more detail here. So this particular house with that small heat pump, the red is basically showing where we have to continue heat with our existing heating system. And the blue is what the heat pump is doing. So this is kind of telling me we could have used a little bigger heat pump maybe. Or, you know, if it's big enough, you might want to have 2 of them. And anyhow, there's a bunch more economics in here. It kind of calculates what your design heat load is for that building based on what you put in there. And now you can be going, okay, well, on the coldest day, I need about 24,000 BTUs. Maybe I'll go back up and start looking for a heat pump that's a little bit bigger that gets me at least closer to that number. And then if we want to just go back and go, well, let's find that current fuel price. What did we say that was?
450, round it up.
450.
Yeah.
And that's without tax, so being generous here. Get back to that calculate button, kind of take all the same parameters. Now you're making a 30% return on your money for the next 15 years. Not a bad investment. Your net present value is $9,000. After you've paid off that unit, you're going to make an additional $9,000. Even though it's a small unit and it's only doing a chunk of your heating load, it really is a significant number. So if that's all you're going to get for now, I say go for it, and then take your savings and look at, hey, Darian, I'm ready for number 2. In a year or something. I think I've got it figured out what I need to do. I'm going to insulate, I'm going to do windows and doors. So anyhow, that's kind of a cool program. And the website is heatpump.cf.
Heatpump.cf.
And you can go there and you can play with this all night long. And you can go, you know, and then you go bug Darian. Going, you know, because we could have gone back up there and changed heat pumps and gone to a bigger one and done some comparisons and stuff. Does that make sense? It's there to play with.
Yep.
Use it. Like I said, it's got our weather data in it. Now I have to get back to where we were.
Do you know if this model, like we were saying, that probably electricity will gradually go up to?
Go to share from current slide.
Because this is looking at heat pump over 15 years, that the cost of electricity will gradually be going up.
Well, if you think of oil, the majority of the cost of a gallon of oil is really related to what we're paying for a barrel of oil.
Okay.
Electricity, it really is only a small part, even though natural gas and quick inlet may go up a bunch. The vast majority of our electric bill is that generator and the transmission lines and our distribution lines. Those are all kind of fixed that are just going to go up with inflation, right? That's just day-to-day stuff. that little extra from the natural gas price isn't gonna do what oil does. Not to say that it is gonna go up. I mean, there's kind of no doubt about it.
Just, it goes up anyway,
Right,
whether you get a heat pump or not.
right. But if you're tired of the roller coaster, I'm here to tell you that you're gonna see a whole lot less go on over the years, and you can actually predict probably electric rates a whole lot better than you can oil. So just to kind of show what I've been doing over the last 4 or 5 years, this is my first Chinese air-to-water heat pump that I bought. I got it from the east coast of Canada and had it shipped all the way to Alaska because I couldn't find one anywhere else. Efficiency wasn't, that COP wasn't all that great. I think I heard it a little bit, not knowing what I was doing. Over a few times, I had a few issues. Here's the heat pump I got in right now that Darian kind of helped me put in. You know, the COP, that seasonal efficiency, much better. And I've been running a little bit cooler this past year, and it actually goes up because if I don't maintain 110 degrees, I'm only maintaining 100 degrees. It actually just shifts that efficiency up that amount. So it's that whole battle of going, how cool of a water can I use and still get by? So this Fujitsu, that was my first air-to-air mini split that I put in. And you can see where, it's kind of a little rough here. I don't know what happened during this 36 degrees, but it got real happy for a little bit. And then it just kind of flattened out. And actually it got worse. I can show you another graph because it did not like being in my little house. It just started cycling and it was just not a happy camper. I then put in this Gree, the huge Chinese heat pump manufacturer. And you can see where it kind of started just fine. And it really did what you kind of expected as it really got warmed up. It didn't have to work very hard, and its COP went up really nice and high. So it's very difficult. These air-to-air heat pumps are almost impossible to measure the true efficiency of them. We can measure the power that goes into them easily, but then we have to figure out how much heat is coming out of that indoor unit. So you have to be able to accurately measure the temperature across that face. You have to be able to accurately measure the flow of air coming out of those things. And it turns out it's very complicated. I cheated on my little apartment. I had vacant in the winter, and I was able to shut off the heat pump, run straight electricity, which I knew what the efficiency was, and then turn on the heat pump for a day or two, then go back to straight electric. And we did that over the course of a winter, and we could really come up with a pretty good, accurate number. This is my air-to-water heat pump, just in the last November. We went from the high 40s, if you may recall, down to, we got below zero for a few hours out of the year. Again, there's that line. That's the efficiency line. This is the COP over here. And again, this is kind of where it starts getting a little iffy in terms of just pure economics with $3.30 oil. At $4.50 oil, I would just let it run because it's still going to be significantly cheaper. And I just kind of had to show you what I do in my retirement days, sit there and watch my heat pumps.
That's why I moved to the next slide. Okay. Keep going.
Damn it, I could talk about that all day. So again, sizing is critical. You know, if you put in too large of a unit, which is what I did with that first air-to-air heat pump, that Fujitsu, and it just couldn't handle that such light a load at even cool temperatures. And too small, you're just losing some potential there. It's still going to work fine, it's still going to save you a bunch, but you kind of left a little on the table. And this is kind of what was happening with that heat pump. You know, it would kind of cycle, and then it would kind of purr along for a little bit, and then it would lose it, and then it would turn off, and then it would turn on, and then it would turn off, and it would turn on, and it just never really found that comfortable spot, because they're supposed to be able to vary it based on your load, and they're supposed to magically find where they can put out the exact amount without raising or lowering the indoor temperatures. Well, it just did not like my house. And so here's kind of what happened is when it was cold outside, you know, day, solar, whatever, kind of varies a little bit, but it was going up that line. And then kind of around 32 degrees or so, the efficiency just fell off. Of course, I got on the phone to Fujitsu and got their head, one of their main tech guys. They sent me some wired remote controller, and that helped a bunch. But here's what their manufacturer says the COP should have been on this unit. And here's what I was getting, 2.5, and then back down. And they were claiming at 10 degrees they should have been up at 3.5, 350% efficiency, and just climbing. That HSPF number said that was saying we should have been around here. So it was kind of disappointing. So here's the Chamber of Commerce. We got a power sensor on them. And you can see where their heat pump was kind of having problems. I kind of grabbed a section where it was both good and bad. And then this is what you want to see. It just kind of purred along, kept the temperature just right. And then it lost it again for a little while and was trying to find it. And they got a little bit more smarts, I guess. And I don't know what that is. Is it just their expansion valve not?
I think their outdoor unit's pretty dirty.
Is it?
Do some maintenance down there, just get an air compressor and blow it out.
Well, clean it out a little bit. Yeah, we'll get into maintenance, so, yeah.
And I know I've been down there a few times and checked those filters on the indoor unit, and they're caked full of dust, and that really doesn't help anything. So you gotta check them filters.
Oh my God.
That's what I want to buy and retire in. They can keep me out of trouble for a long time.
How quiet are those pumps? Are they pretty quiet?
On the inside, on the outside?
Yeah, more on the inside.
Yeah, they're very quiet on the inside.
They're much more quiet than the Toyo stove.
Your refrigerator's definitely gonna,
The fan spins a little slower than a Toyo stove, I think, and it's less.
and it's a
just
very
smaller.
super efficient, I mean, they've got a lot of tech into that little blower assembly and stuff. So they went to great lengths to make them very quiet. Outdoor, you know, it's got a bigger fan and that makes a little bit more noise.
And sometimes if you wall mount them like that one, you know, if you got thin walls and stuff, you'll kind of hear the hum out there. So I kind of try to steer people away from going through the wall mount unless you've got a really thick wall or like something to dampen that vibration.
It's in a place where that noise isn't gonna bother you. You don't want it in a bedroom wall, you don't want it
Yeah, you don't want
right up against your couch kind of living room. Anyhow, I always love that little picture again. So we got the outdoor unit that we gotta find a place for. We gotta get power to it. It's a required disconnect switch, so if a service guy has to come, they can disconnect power to it. And like Darian had said, this is brackets that mount on the wall and this thing sits on it. So it's something we gotta think about. I'll show you some more slides. So we gotta find a place for this.
Is that 220 or 110?
Most of them are 220. There's some smaller ones that I've seen are 110, but I think we'll pretty much be seeing 220. Yeah, so it's, you know, you gotta hope the electrician can see a couple extra blank slots in your breaker box, you know, to use. Otherwise, he's gotta do their magic. Breaker panels. So we got this guy, and now we gotta run that line set, those refrigerant lines from this outdoor guy to the indoor one. So you don't want them too far away.
Why is it up high? I would think if you wanted to heat, it would be down low.
I get this one all the time.
Okay.
There's
Snow-
louvers
snow's
on
gonna
that thing that point it straight down to the ground.
Okay, so
I mean,
it's
they
forced
mix,
air.
they do a good job of,
That one's forced air.
yeah, they're up here, there's a nice fan that just, and the louvers, you can point them so they can shoot up or down.
But you have in floor. So-
I had in floor, and that's why I went with the air to water, so I
Right.
could make warm water. Now, my little apartment's got this guy in it,
Okay.
and there, I'll show you a slide.
Which one's more efficient?
I think these air to airs are a little more efficient than my air to water, just because they've sold zillions more of them. I think they got the technology down a little better. I mean, the science really shouldn't be any different
Right.
in terms of the outdoor unit and indoor unit. So the location of all these things, here's one of these. You know, these mini splits were really made initially for air conditioning. That's why they put all of this technology into those upper units. And Darien finds that people don't like using up floor space.
Yeah,
And
that's
they
what I was
do
gonna
mix.
say, like, floor space, you know, you got.
If you're super anal like me, I know that the cooler the air that's going into that thing, the more efficient it is at pulling heat out of those coils. So in theory, this thing would be a little more efficient down on the floor where the air is cooler than up by the ceiling.
And we did that at Lori's house too. I've done it at a few places where you just put them down in a spot where it's kind of out of the way and it's down
Right.
low.
Because we didn't have the room above our big
Right.
windows. We didn't
So-
have the room before the ceiling, but we had the room below the
Yeah.
windows.
So you kind of sensing there's a few trade-offs that are made in this whole little shuffle of where we're going to put the outside one and the inside one.
Can you do a baseboard thing with the two, with the air to water?